Thank you very much for the invitation and for the introduction. So I will today talk about joint works with Shijie Fan. And the program of the talk is as follows. So first, I discuss two classical examples. Then I would like to discuss more explicit examples, so-called ICO equations. Then I will introduce the definition of the non-degeneracy criterion and give the basic idea. And afterwards, I will discuss non-degenerate curves. In particular, I will discuss plane curves. And finally, I will discuss an application to the Fermat problem in a slightly more general setup inside some rational surface. So let me start with the first part. So for this, I would like to discuss some geometric background. And I denote by n the positive integers. And for each I let sigma I be the i's elementary symmetric polynomial. Then I would consider the so-called icosahedron surface, which was studied by Klein in 1873. And this is a surface inside P4 defined by sigma 2 and sigma 4. Then a closely related surface is the so-called cubic diagonal surface of Clebsch, which is also a surface inside P4, which is the sum of the cubes of the coordinates equals 0 equals sigma 1. And the geometry of these surfaces was studied by many authors, and they proved many important results. So in particular, it is known that these two surfaces are rational. So they are rational or birational to P2 over the complex numbers. And then what is important for this talk, somehow some geometric results of Hirzebruch imply that the defining equations of these surfaces, V and V prime, are two classical examples of equations which we call non-degenerate. And now I would like to discuss some Diophantine equations related to these surfaces. For this, I let S be a finite set of rational primes. I let NS the product of all primes in S, and ZS is the ring of S integers inside Q. Then I look at the following equation 1, which is the U of ZS is the solutions of X in sigma, of sigma 2x equals 0 equals sigma 4 of x, and sigma is the set of x in z to the 5, such that the coordinates are co-prime, and actually each three distinct coordinates of x, the GCD, is a S unit. So this will be the first equation, and the second equation is U prime of ZS will be all x in ZS star to the 4, which will be the sum of the x1 cube plus x to the x4 cube equal to 1 equal to sigma 1 of x. And the question then is, what is the relation to these varieties V and V prime? And one can show that actually these sets U ZS and U prime ZS are the S integral points of the following two varieties, U and U prime. So here U is we look at V and we remove 5 points. So we remove the 5 points given by the permutation of the coordinates of this point 1, 0, 0, 0. And U prime is given by V prime minus a divisor D, where D is the union of the 5 coordinate hyperplanes V plus Zi. And then we can compare U and U prime. So for example, equation 1 is more fundamental than equation 2, since the variety U is much larger than U prime in the following sense. So one can, for example, show that there exists some open immersion phi, which is defined over Z13. And this open immersion, when we look at the image, then U prime is actually isomorphic to V minus D, and this is strictly contained in U, and U is just V minus Z. So we see that U prime essentially is given by V minus a divisor, so minus a curve, and U is given by V, and we only remove 5 points. And then also what is useful for Diophantine problems is that this open immersion is compatible with heights. So next, I would like to discuss some Diophantine results for these two Diophantine equations. And the first remark is that actually both of these sets U prime of Q and U of Q are very large, because both surfaces are actually rational over Q. And then one can apply a highly uniform bound for the number of solutions of the generalized unit equation, and then one obtains the following theorem 1, which is a special case of Evertse, Schlickewey, and Schmidt. And it gives that the number of solutions, so the cardinality of this set U prime of set S, so the number of solutions of this Diophantine equation here is explicitly bounded only in terms of the cardinality of S. So this bound only depends on the size of the set S, but is independent of the size of the primes in S. Then one can also ask the following question. So we look now at a subvariety W prime, which is strictly larger than U prime, but is still strictly smaller than V prime. And we look at the S integral points of such subvarieties. And then there are very strong and essentially optimal non-degeneration results due to Corvaya and Zannier for S integral points on smooth cubic surfaces. And these results imply in particular the following theorem 2. So this will be a special case of Corvaya-Zannier. And they show that the points W prime of ZS are not Zariski dense if W prime is the following variety. So we look at V prime, but now we only remove two hyperplanes, so V plus Z0 and V plus Z1, while before for U prime we removed 5. So next I would like to discuss what can we say about this set U of ZS and for this Diophantine equation. And here one can use explicit bounds for the height and the number of S integral points on coarse Hilbert moduli schemes, which were obtained by Arno Kret and myself. And we proved the following bounds. So we showed that the number of solutions of this Diophantine equation is bounded only in terms of this NS. And we also showed that any solution of this Diophantine equation here has height bounded explicitly only in terms of NS. So here one can use, for example, the following explicit constants. And also here, small h is the usual logarithmic Weil height on P4. So this variety U can be viewed inside P4. And I also would like to remark that actually this theorem 3 also holds for U prime in place of U. So we can just use this open immersion phi, and we can also use that it's compatible with the heights. Then we get as a corollary the same result for U prime in place of U. And another remark is also that this theorem 3 is optimal in the sense that we cannot make the variety U larger inside V. So for example, we cannot remove maybe only 4 points. So if you only remove 4 points, then this set here can be infinite. So next, let me briefly discuss some aspects of these results. So maybe the first remark is that the first two theorems hold for any number field, and theorem 3 actually only holds for k equals to q. And another remark is that the proof of theorem 3 actually doesn't allow to study the much more difficult set W prime of set S. And also the bound we get here for U prime of set S is actually much worse than the bound we get in theorem 1 from Eritzer, Schlickewey, Schmidt. Then I also would like to mention that theorem 1 and 2 use Diophantine approximation techniques, which usually allow to prove deep properties of the solutions. But so far it's not clear whether they can also explicitly bound the height of all solutions. And finally, also it's not clear whether Diophantine approximation techniques can be applied to this set U of set S. So since the relevant divisors in the singularization of this surface V of Q are never big, and so in particular also never ample. So next, let me discuss some more explicit examples of non-degenerate equations. So these are so-called ICO equations. And for this, I have to introduce some notation. So I let f be a polynomial which is homogeneous of degree n greater or equal than 1. It has coefficients in z and in 4 variables and 5 variables. Then we can look at xf inside P4, which is defined by sigma 2, sigma 4, and f. Here again, sigma I are just the i's elementary symmetric polynomial. Then we can describe the Q rational points of xf in the following way. And also we then can introduce the following non-degeneracy criterion. So for this, we introduce this degeneration delta, which will be the product of all AI, where we take the product of over all 5 diagonal coefficients, A0 up to A4, of this homogeneous polynomial f. So f has degree n, so then we can write it in this form, and then the diagonal coefficient is just the coefficients ai in front of xi to the n. And then we can say, or we call this curve xf non-degenerate if this delta here is non-zero. And then the relation to non-degenerate equations is as follows. So we look now at these three equations, sigma 2 equals 0 equals sigma 4, f equals 0, where f has this degeneration delta here is non-zero. And these are all explicit examples of so-called non-degenerate equations. And now we can state the first theorem, so this theorem A. So we assume that this delta is non-zero, then we can explicitly bound the cardinality of the number of rational points of xf, and we can also bound for each rational point x of xf, we can bound its logarithmic Weil height explicitly only in terms of the radical of delta. So here the radical is just the product of all primes dividing this delta. And here hx is explicitly is just the logarithm of the maximum of the absolute value of the coordinates. And we can take, for example, these explicit constants here. And also I would like to remark that the locus where this delta is non-zero is open inside the moduli space of all these curves xf. And so in particular, almost all of these xf are non-degenerate. And then one can somehow use this for applications in the following way. So I can use that actually these curves xf are fundamental in the sense that actually any curve x over q of genus greater or equal than 2 is birational over q into some xf. And then because we know that actually almost all of these xf are non-degenerate, we can then use this theorem A to prove the so-called effective Mordell conjecture for large classes of explicit curves x over q. So I will explain this application later in the talk. And next, I would like to discuss the general definition of this non-degeneracy and explain a little bit the basic idea. So this will be the third part. So for this, I fix mn will be positive integers. I fix the I inside 1 to the m. And also I fix some polynomials fi, which are homogeneous of degree greater or equal than 1. Then we call the equations f1 equals 0 up to fm equals 0 non-degenerate if the projective variety defined by these homogeneous polynomials inside Pn over Q satisfies a certain geometric non-degeneracy criterion. And here, the non-degeneracy criterion requires some terminology or moduli terminology, which I will not introduce in this talk. And I will just try to focus somehow on the key property and also try to explain the idea why this definition is useful and what one can do using this definition. So let me now explain the key property of this non-degeneracy criterion. So if V is non-degenerate, so it satisfies this criterion, then there exists some open-dense subset U of V, which is a so-called coarse moduli scheme of finite level. And roughly speaking, this means the following. So this means that the Q bar points of U are in bijection with pairs of isomorphism classes A alpha, where A is some abelian variety of dimension G, and alpha lies in some finite set P of A. So here AG is just all abelian varieties over Q bar of dimension G. Then G is a fixed number greater or equal than 1. And this PA is some finite set associated to the abelian variety A over Q bar. So in other words, somehow this UQ bar parameterizes so-called semi-abelian varieties, which are actually non-degenerate. So the idea of non-degeneracy comes from this property. And then why is this interesting? So one can try to use then such non-degenerate varieties to study subsets of solutions of the Diophantine equations Fix equals 0, which this set here identifies just with the Q rational points of the variety V. And the idea is somehow we can decompose the set of Q rational points into two subsets. So we look at the Q rational points of U, union of V minus U of Q, where this Q rational points of U, we can write it as the pre-image of some map phi into AG. The image, and this phi here will be some map to AG, which is simply the forgetful map. So we can look at UQ, we can view it inside UQ bar, and then because we have this parameterization here, or this modular interpretation, we get a map actually from UQ bar just by forgetting here the alpha of A alpha, we send it to A. So this is a so-called forgetful map. So we get a map to AG, and then we can write this set as the pre-image of its image. And then the advantage in some situations is as follows. So this set here is usually simpler than this set here, since the dimension is strictly smaller. So for example, this v minus u is automatically finite if this v is a curve. So for example, if m is 1, n is 2, then this v is of this form. And then we know that actually this set is automatically finite. And so somehow this gives, in certain situations, can give some advantage. And then one can also somehow is reduced to study the abelian varieties which lie in the image here of uq under this map phi. And so next, I would like to discuss some strategy to prove explicit height bounds using this definition. So suppose that we are given non-degenerate equations, then V is the variety defined by these equations, and H is the logarithmic Weil height. And then we would like to, for a subset of solutions of these Diophantine equations here, we would like to bound this height H on S. So that's somehow the goal. And then for this, we can try to use a strategy which was developed over the last 70 years by many people. And it combines the method of Faltings, Arakelov, Parsin, Szpiro with modularity and Masser-Wustholz isogeny estimates. And now let me give a very rough outline of this strategy. So essentially there are two steps. So the first step is the so-called effective Parsin construction. So one has to control this height H on the points outside U in an explicit way. And one also has to try to show that the forgetful map here, phi, which goes into AG, somehow is compatible with heights. So we need that the height H of X is bounded explicitly in terms of the stable Faltings height of the image phi of X for all Q rational point X in UQ. And here, this H of S is the usual stable Faltings height on AG. So this will be the first step. And the second step is called effective Shafarevich. So then we have to try to bound this stable Faltings height on this set curly A, which is the image phi, where we look at S intersecting U of Q. And for this, one can try the following. So the first step is completely unconditional. So one can control the variation of the stable Faltings height in an isogeny class for each A in this curly A by combining a formula of Faltings with deep Masser-Wustholz isogeny estimates based on transcendence. And for example, here one can use the fully explicit version of Gaudron and Raymond. Then with this first step, somehow one is reduced to control this stable Faltings height on this set A, but only modular isogeny. So we can move around in isogeny. We have to construct in eta isogeny class 1 abelian varieties with bounded heights. And for this, we can combine the geometric version of modularity, which usually uses the Tate conjecture proven by Faltings, with some average Kolmez formula for abelian varieties with CM. So this was proven by Yuan Zhang and independently by a group of 4 other mathematicians. One can also use explicit analytic estimates and explicit results from Arakelov's theory. And so this is somehow, it doesn't work in general for all, but in some situations, for example, in the GL2 case, this is unconditional using Serre's modularity conjecture and some GL2 type constructions and some Bailey degree results. So now, next, I would like to discuss some applications in which situations one can actually use this strategy to prove explicit height bounds. So again, I assume the F1 to Fm are non-degenerate Diophantine equations. Then this V, this variety V, contains an open dense U, which is a coarse moduli scheme of finite level. And then the strategy currently can be applied in the following situations. So the first situation is when this U over Q is a so-called moduli scheme of GL2 type. So this just means that the abelian variety parametrized by U are all of GL2 type. Then this was extended in a joint work with Arno Kret. So then we showed that we can actually assume that U over Q is a Hilbert moduli scheme. So in some sense, it's a more special than these situations, but also has some more structure. So here we assume the A have all real multiplications. And then this was further extended in joint work again with Arno Kret. So we showed that actually U over Q is just a coarse Hilbert moduli scheme with empty branch locus. So somehow here we only know that the Q bar points parameterize such pairs. And also there's some technical extra condition is satisfied that the branch locus is empty. And then one can, for example, look at the following example. So the first example is then V and V prime are the Clebsch-Klein surfaces discussed before. Then another examples are these ICO curves XF which are non-degenerate, so like the delta is non-zero. Then one can also look at all plane curves inside P2, which satisfies some criterion tau, which we will discuss in part 5 of the talk. And one can also construct many more examples, but for these examples, somehow one needs to still work out this effective Parsin step A. So for example, if one knows there exists an abelian scheme A0 over U of GL2 type, then one can apply this strategy, or if one knows that U has a quasi-finite morphism to some representable Hilbert modular variety over Q, then one can also apply the strategy. And I also would like to mention that Levent Alpog, he had a lot of examples in his PhD thesis, including some very nice explicit family, in which he actually studied the problem of constructing many curves where V is equal to U and satisfy, for example, this GL2 or H, these two conditions. So next, I would like to discuss or illustrate this notion with non-degenerate curves. And for this, I write for AN over Q, and Pn over Q, and I let X be a curve over Q. So for example, if F is a polynomial of degree greater or equal than 1 with coefficients in Q, then its zero set X inside A2 is a curve over Q, such that the Q rational points is given by these solutions of this equation fxy equals 0. And then a classical result says that actually each irreducible component of X is birational over Q into some plane curve V of F in A2. And on using classical construction of Clebsch and Klein, we obtain the following analog. So each irreducible component of X is birational over Q into some curve XF. And then we can make the following definition. So if X is actually birational into some curve VF, then we call VF plane model of X. And similarly, if it's birational over Q into some curve XF, then we call this XF an icomodel of X. So now let X be a curve over Q. And then by theorem B, we know that each irreducible component of X has many icomodels XF. So we can define or get the following non-degeneracy criterion. We say that X is non-degenerate if X has at least one non-degenerate icomodel XF. And again, the notion to non-degenerate equation is as follows. So if X inside Pn given by this F1 to Fm is a non-degenerate curve over Q, then actually the defining equations are examples of equations which we call non-degenerate. And also again, as almost all XF are non-degenerate, there exist many non-degenerate curves X over Q. So one can ask the question, what is the relation of this non-degeneracy property to the property that the curve X has genus greater or equal than 2? And that we can prove the following theorem C. So if X is non-degenerate, then X has genus greater or equal than 2. So let's recall the theorem C. And also this somehow the converse of this theorem is the following open problem. Problem degenerate. Determine which curves X over Q of genus greater or equal than 2 are non-degenerate. And somehow we already saw some examples. So these curves XF and delta is non-zero. Then we will see some examples later in the talk, which satisfy some criterion tau. And maybe now let me explain next how to get height bounds for rational points on such non-degenerate curves. So we let X be an integral curve over Q, and we assume X is inside Pm and is quasi-projective over Q. And we also let H be the usual logarithmic Weil height on Pm. Then we get the following theorem D. So suppose that X is non-degenerate. So then we know there exists such an icomodel XF of X, which is non-degenerate. And for any such model XF, there exists a controlled open dense U such that all Q rational points of U have bounded in the following way. So let me explain these quantities here. So this nu of F will be just the radical of the delta. So the delta will be defined in terms of this icomodel XF. Then we have these two explicit constants. And this d of x will be the product of 2 degrees. So the degree of the normalization x tilde over x and the degree of the closure of x inside Pm. Then also h of x will be some height of this normalization x tilde inside P4 times Pm. And this U, which is controlled open dense, has the property that it's, in some sense is the largest open subset of X with an immersion inside XF. And now let's apply this theorem D. So this theorem D gives bounds for all Q rational points of U, but we would like to have bounds for all X in X of Q. So then one can proceed in the following way. So one can try to construct such an ICO model XF, such that this nu of F, so this radical here of the degeneration delta is controlled. And one also has to control the points outside U. And let me emphasize that both of these problems here are geometric problems. And to illustrate somehow this application of theorem D using this 1 and 2, I will next consider a special class of non-degenerate plane curves which satisfy some criterion tau. So this will be the next part. It will be now studying plane or equations fxy equals to 0. And for this, I will introduce this criterion tau. And the motivation somehow is the following. So we introduce this criterion for plane curves in order to explicitly produce large classes of non-degenerate plane curves. So let f be a polynomial in two variables of degree d greater or equal than 1. And let's consider x inside A2, which we can view inside P2. And then we have the following criterion tau. So tau will be an explicit rational map over Q, which we define in the next slide. And this EI will be 5 permutations of the point 1, 0, 0, 0, 0. And then the criterion tau says that we look at the closed image, tau of x, we take the closure, contains none of these 5 points. And I should also mention that the rational map tau is birational onto its image. And also for any given f, because this tau will be given explicitly, one can actually compute whether this criterion holds over Q or over C. And then the next result says that if x satisfies this criterion tau, then x is non-degenerate. And again, the relation to non-degenerate equations, essentially, if this criterion is satisfied, then the homogenization fh equals 0 gives an example of a non-degenerate equation. So also here, I give the definition of tau. So for what follows, it doesn't matter precisely what are the polynomials. So they are not simple, but also not too complicated. And they define such a morphism from P2 to P4. And so now the advantage of this criterion is that we can actually construct large classes. So for this, we take a n, and we define a number r, which is 5 when n is 1, and which is of this polynomial form here if n is greater or equal than 2. Then we obtain the following theorem fi. So for each n, there exist r explicit polynomials fi in qxy, such that these r polynomials are q-linearly independent, and for each coefficient vector c in q to the r, such that the first 5 coordinates are non-zero, this plane curve defined by this coefficient vector, so ci times fi, we take the sum, inside A2, satisfies this criterion tau, which we described earlier, and the degree of this curve is 12m. And this fi can be computed directly in the following way. So one can simply take fi is, if this small fi evaluated at these polynomials tau 0 to tau 4, well, the small fi are monomials of degree n, which form a Q basis of this quotient ring, of the nth part of this quotient ring, such that the first 5 of these small fi are given by xi minus 1 to the n. And now I would like to discuss a conjecture. So for this, again, I let f be a polynomial of degree d greater or equal than 1 with coefficients a iota. And I said absolute value of f is just the maximum of the absolute values of the coefficients of f. Then if x has genus greater or equal than 2, then the Q rational points, the set of Q rational points is finite by the Mordell conjecture proven by Faltings in 1983. And then using this finiteness, one can motivate the following conjecture EM, which says that if x has genus greater or equal than 2, then each solution of this Diophantine equation fxy equals 0 has height bounded explicitly in terms of this function here, where c of d and kappa of d are effective constants depending only on d. So here by effective, we mean that this is just the iterated exponential in terms of d for some explicit n. And also this small h here is the usual logarithmic Weil height which I briefly recall here. So it's just small h of x is just the logarithm of the maximum of the absolute values of m and n for any x in Q. And then I would like to discuss some known results. So we can also look at the integral analog of this. And this was established by many authors after Baker's breakthrough using linear forms in logarithms. And they proved the S-integral analog of this conjecture for large classes of explicit curves actually over any number field. And one can, for example, look at the excellent books of Baker-Wustholz, so also of Everett-Segueri for overviews. Then also, I would like to mention that some recent work of Corvaya, Lombardo, and Sanier. So they made important progress on this S-integral analog for large classes of genus 2 curves over any number field K. And then also, if one has some more information about certain ranks, for example, about the Mordell rank of the Jacobian of these curves, then there are very powerful methods, like for example, Chaboty's method, which give strong Diophantine results for this set X of Q. And actually, these results often allow not only to bound the height, but I can really determine all the solutions. And of course, when you have all solutions, you get the optimal height bound in some sense. And these methods usually work very well in practice for a given F. And also some of these methods actually also work for certain families of F. So here I mentioned some work of Viada, Ceccoli, Veneziano Viada, and Veneziano Viada. So they proved for certain families of growing genus over any number field, they proved some sharper version of this conjecture. And they used this theory of anomalous intersections of Bombieri, Masser, and Sanier. And their bounds actually also in some cases allow them to determine the set X of Q. And so now I would like to apply our height bounds for non-degenerate curves to this conjecture for the curves which satisfy this tau. So I take such a F polynomial of degree D greater or equal than 1. And I suppose that the curve X satisfies this criterion tau. Then the curve X over Q is non-degenerate, and the number of Q rational points is bounded by this function explicit bound here. And all solutions xy in Q squared of fxy equals 0 satisfy the following height bound, where the constant C of D and kappa of D depend only on D. And here this K of D, this appears here in the bound for the number of solutions. And here, again, absolute value of F is as before, and small h is as before the usual logarithmic Weil height. And then one knows that each non-degenerate curve has genus greater or equal than 2 by this theorem C, which I stated earlier. Then this corollary proves this conjecture EM for all curves X which satisfy this criterion tau. And also, we constructed in theorem Fi, we constructed large classes of such explicit curves which satisfy tau. So for example, one can use these results to show that the space here of dimension R, which is roughly 4n squared for each n in Z greater or equal than 1, parameterizes such explicit curves X in A2 which satisfy tau and have degree 12n. Then also similarly for each odd square G greater or equal than 2, there is a moduli space of dimension more or less G, which parameterizes such curves of genus G. So next I would like to discuss the question somehow, can we actually also determine this set X of Q, at least for some very special explicit families of curves. So I introduced the following family F of C. For this, I let C be some coefficient vector with 5 entries. And I consider the family F of C, which will be all polynomials, which are linear combinations of this FID, where this Fi will be just, we look at these polynomials tau I, which I defined earlier, but we evaluate the Z coordinate in 1. And then one knows that actually these Fi are Q-linearly independent. So we look at this family, and we would like to study the set of Q rational points of curves in this family. So we let F in F of C, then we look at the curve X in A2, and then we know that the genus is greater or equal than 2, and the degree is equal to 12D. And also one can show that actually the Q rational points X of Q always contain this set T given by these 4 points. So 0, 0, 1, 0, 0, 1, 1, 1. And also if the degree of F is not too large, then actually this set X of Q often contains additional solutions. But somehow if the degree gets larger, it's harder and harder to find these additional solutions. And then one can ask actually what happens if the degree is large of f? Does it always holds that there are no more additional solutions? So x of q is given just by these 4 points. And on using our results or combining them with some techniques from Diophantine analysis and Diophantine approximation, and we obtain the following answer to this question. So we fix again some coefficient vectors c, and then for all f in this family f of c with degree greater or equal than dc, we actually get that the q rational points are given by this set t. And here this dc we can actually write down explicitly. So it depends on the radical of these ci's, and it depends on the absolute values of these ci's and some huge absolute constant. And then the application somehow for this is that for some infinite families of curves, x of c of genus greater or equal than 2, we can actually completely determine this set x of q, which is just given by these 4 points. So somehow this is a very special family of curves, so we would like to have similar results for other curves which satisfy tau. And for this, somehow we have to look at the following problems. So we would like to compute this set x of q when x satisfies criterion tau. And for example, one can try to use these powerful practical approaches which were developed over the last decades. And this usually requires to control some involved ranks. And maybe a good survey or excellent survey of this can be found in some paper of Balakrishnan and other people, where they describe many of these approaches. And one can also try to compute this x of q using the following 2 approaches. So the first of these approaches is somehow just an algorithmic version of the strategy of proof of corollary EM. And another approach is somehow more naive. It's just we search for all points of bounded height, but we need some efficient sieves using Diophantine approximation techniques. And maybe let me make some remarks. So combining explicit height bounds with efficient sieves has a long tradition. So for example, a very nice result of Baker-Davenport is that they completely solved these 2 Diophantine equations using huge bounds based on logarithmic forms and combined it with some Diophantine approximation technique. And another thing is that actually if this sieve here in 2 is strong enough, then actually the computation of the solutions usually becomes in practice independent of the huge size of B. So B can be huge, very large. If it's not too crazy large, then and the sieve is strong, then it somehow doesn't matter too much the running time of the algorithm or the sieve to compute all solutions. And so let me now maybe quickly discuss these 2 approaches here. And so the first is this algorithmic version of the strategy. And maybe let me just briefly mention somehow the idea is that instead of estimating the height or controlling the height in each step, one tries to compute the objects in each step. And in practice, somehow this one has to overcome various computational difficulties. So for example, to compute here in this step, the underlying automorphic forms or modular forms can become quite challenging. And also many other steps become difficult in practice. So this somehow gives the new problem, which says like, make this algorithmic strategy practical, at least for some small f. And this seems to be a difficult problem. But I would also like to mention that somehow in some much easier situations, when, for example, the solutions are integers and also some are simple equations, then one can use somehow some simpler version or easier version of this algorithmic strategy using Cremona's algorithm to compute modular forms, to compute for some very few equations, one can actually compute the S integral points or the integral points. So next, I would like to discuss this approach about the height bounds. And here, somehow the idea is we have such an explicit height bound B, and we just look for each element in this set SB, which is a finite set, whether it actually lies in X of Q. Then of course, if the height bound is too large, even if you kind of can optimize it a bit, and this will never work in practice. So we need somehow some efficient sieves to search more efficiently for this set X of Q inside SB. And so this gives us another problem that one try construct an efficient sieve for XQ inside SB for these curves here which satisfy tau. And one approach is one can try, for example, use techniques from Diophantine analysis or approximations to solve this problem, and then use the sieve to compute this combined with the height bounds here. So somehow a naive example of this type is this computation I mentioned earlier, that x of q is t in this family x of c. But however, somehow these curves are very special, and somehow new ideas are required to solve this algorithmic problem here and for other classes of curves. And somehow the hope is that maybe also some techniques for other more classical Diophantine equations can be used to study this problem. And for this, I would like to mention also some more classical equations which have efficient sieves. So for example, one can look at two Euler equations for which one knows efficient sieves, or S-unit equations, or Mordell equations. And for all these, many people developed efficient sieves, and these efficient sieves can be defined essentially with any explicit height bound. So it doesn't matter how big the explicit height bound is. There are also several methods which give explicit height bounds. For example, like logarithmic forms, or we can use Diophantine approximation, or we can also use modularity to get height bounds for some of these equations. And all these height bounds somehow, if the sieve is strong enough, then somehow it doesn't matter for the running time to compute all solutions. And the hope is that in the future, maybe one can also use such efficient sieves for the q-rational points of these curves which satisfy criterion tau. Okay, so maybe in the last part, let me now focus on this so-called Fermat problem. And I would like to discuss this Fermat problem inside some rational surface. So I write Pm for Pm over Q, and I let F1, F2 be two polynomials homogeneous in 5 variables, so that they define a surface S inside P4, which is a projective rational surface over Q. And then we can look at the set S of Z, which is essentially all the solutions x in z to the 5 of these two polynomials f1, f2, and the GCD of the coordinates is 1. Then we call a point x trivial if all coordinates lie in this set -1, 0, 1. And also we write again n for the integers greater or equal than 1. Then for any ABCDE non-zero, one can try to construct the n0 such that the solutions of the Fermat equations are trivial when n is greater or equal than n0. And here the Fermat equation in P4 has 5 variables, and we have coefficients a, b, c, d, e, and we look at all solutions which actually lie in this rational surface S. And then, for example, one can show, because the set SQ is kind of large, that this problem is non-trivial. So one can always construct for each n some coefficients such that this Fn has a non-trivial solution. So this means that n0 has to depend on the coefficients. Then also one can study the problem for which rational surfaces this problem actually makes sense. And on using some higher dimensional version of this Masser-Wustholz ABC conjecture, one can give a conjectural description for the rational surfaces for which one can somehow expect the positive answer to this problem. And next, I would like to discuss the classical case and the ICO case of this problem. So the classical case is we have S is P2, which is a rational surface by definition, and we can view it inside P4 by just taking the last two coordinates 0. Then the problem F is the classical Fermat problem, which was solved by Wiles for the coefficients A equals B equals minus C equals 1, and he obtained the optimal exponent n0 equals 3. And the proof was then completed in a joint work with Richard Taylor. And now we would like to replace this surface S, P2, by some other, somehow by rationally equivalent surface. And then we take this icosahedron surface, S ico, inside P4, given by sigma 2 equals 0 equals sigma 4. And then theorem A, combined with Diophantine approximation techniques, actually allows us to solve this problem F when the surface S is equal to S ico. So we obtain the following corollary F. So we assume the rational surface is S ico, then all solutions have bounded height depending only on the radical of these coefficients A, B, C, D, E, and we have some explicit constants here. And moreover, we can show that then there exists actually the n0, such that all solutions of Fn are trivial when n is greater or equal than n0. And I would like to mention that the analog of this corollary is still open for general non-zero ABC in the classical case when S is P2. But on the other hand, in the classical case, for many ABC, optimal results are known. And often these results actually hold in much more general situations. So for example, in the classical situations, people can take different exponents and they can actually solve the analog of this Fermat problem with an optimal exponent, N0. And maybe if a nice overview can be found in some paper of Bennett, Mihailescu, and Zizek in some open problems in mathematics. So I recommend to have a look in this survey. And also, as a remark, somehow the underlying geometry of this problem F is equivalent in some sense. So because of this, somehow it gives some motivation that also this problem F should behave similarly for different rational surfaces. And maybe there's even some relation between these different rational surfaces of the Fermat problem. So next, I would like to discuss somehow the optimal N0 in the case S is S ICO. So recall our corollary. And this motivates somehow what is the optimal, the smallest N0, such that all solutions of Fn are trivial when n is greater or equal than N0. And so the next result doesn't solve this problem, but at least it gives an explicit upper bound for the optimal N0. So we can actually improve this corollary F a little bit, and we can say like this corollary F actually holds when N0 is this explicit bound here, where this B is given explicitly here, and this mu is just the maximum of the absolute values of the coefficients. And then, in some sense, using the bounds in this corollary and this corollary, one can just search in principle for all solutions. And then if one is larger than these bounds, one knows, okay, this is the optimal N0. But of course, in practice, again, this doesn't really work. And one needs, again, efficient sieves to find this optimal N0. So finally, let me also discuss the case of number fields. So let K be a number field. And by mu, I denote the roots of unity. Then we say that the point in P4 over K is trivial if the point has coordinates xi such that all xi lie in mu union 0. Then we take again S is a projective rational surface over K inside P4. And then we say that Fermat holds inside S over K if for any choice of coefficients A, B, C, D, E in OK, so OK is a ring of integers in K, non-zero, there exists such a N0 such that all K rational points of X and K are trivial when N is greater or equal than N0. And here Xn is just this defined inside S given by this Fermat equation. And then in the classical case, again, very strong results are known for many ABC triples and large classes of number fields. So there's some very nice results of Jarvis-Mikin. They solve it, I think, over Q squared of 2. And also more recently, there are some very nice results of Freitas-Zizek, which studied this problem over totally real fields. And many more results also more recently. So finally, let me also discuss the ICO case. And so K is an arbitrary number field, mu is the roots of unity. And somehow, in the case of S ICO, it can happen that the Fermat problem fails over certain number fields. So to somehow classify those failing number fields K, we introduce now some explicit criterion which involves two linear forms. So we look at the linear form L is 1 plus x1 plus x2, and M is equal to 1 plus x3. And then we can look at the following criterion mu, which somehow we look at a certain set which depends on the roots of unity mu in this number field K, and some polynomial equations need to be satisfied. Also, the Lm needs to be non-zero, L over M is not in mu, and if this set here, which depends only on the roots of unity of K, is empty, then we say this criterion mu is satisfied. And here, for this notation here, we just, for a polynomial f, we just say f of 3, it's just we take f, and then inside, we just take the third powers, so x1 to the 3 and so on. And then I also would like to mention for any given K, one can compute the roots of unity, and then I can also compute whether this criterion mu here is satisfied. So for example, one can easily show that K, number field K satisfies this criterion mu if the root of unity is just plus minus 1. So for example, if K has a real embedding into R. Then also the number field K satisfies this mu in the range when the degree is at most 10. Then it's always satisfied, except when maybe the degree is 6 or 8. But if the degree is not 6 and 8, at most 10, then this criterion is always satisfied. Then also, somehow the smallest field where this criterion fails is when we look at the 9th root of unity and then look at the field generated by it, and this fails this criterion mu. And then on using a variation of the strategy of our proof of corollary F and corollary F plus, we can actually, for any number field, give a complete answer to this Fermat problem, or whether the Fermat holds inside S ico over K. So we obtain the following theorem F. So we obtain that the Fermat holds in this surface S ico over number field K, if and only if this K satisfies this criterion mu. And I should also mention somehow the underlying strategy of proof is robust in the sense that it allows substantial generalizations in various directions. But one difficulty somehow when the number field is not Q is that it's not possible to explicitly control here the N0. So we have no control over this N0. We just know it exists. And then this gives us somehow the final problem of this talk is problem F plus. Try to explicitly control this N0 in terms of the number field K and the coefficients A, B, C, D, E. And I think that I'm now at the end of my talk, so thank you very much for your attention.